So as we've been talking about this planar kinematics, this kinematics of a rigid body, we said there are typically three things we have happening. We could have translation, where the body is just moving. We could have rotation, where the body is rotating about some fixed axis. And then finally, we could have general plane motion, which is usually some combination of the two. So like my pen, let me use a brighter pen here that you can see a little better. My pen moving and rotating at the same time as it moves through the plane. So this general plane motion that we're going to be talking about in the next several videos, because this is our most complicated form of our motion that we're going to see in our planar kinematics. So in this video today, we're going to start with general plane motion in an absolute analysis. And this usually isn't the most common one we use, actually. Typically, when we're talking about general plane motion, you have a few options you can use. You can do absolute analysis, as we're going to talk about in this video, or you can do a relative motion analysis, kind of like we did when we talked about particles. And when we were doing absolute analysis, we were typically looking at pulley problems more than anything. And then our relative motion analysis, we were able to do a little bit more. And that's kind of the same concept that we have here coming in with our planar kinematics, is we're going to have the option to do absolute or relative motion. And relative motion is going to be there's a lot more to it. It's a lot bigger breadth. It'll let you do a lot more. But we'll talk about this absolute motion analysis just so you can kind of see it in case it ever comes up for you in the future. So this absolute motion analysis, really what we're doing is we're using it for some thin slab that is translating and rotating in the plane. And where we commonly see it most, I would say, is if you have some slab, something that is pin connected to something else, where you have an angle that's changing and a length that's changing. So like if I have two bars that are connected together, one of them is getting longer and one of them is rotating. So maybe they look like this, and then this bar gets longer, and this bar rotates up more. So now it's at a new angle theta. Here's S2. So for our absolute motion analysis, we're really pretty restricted to when we're looking at it in an absolute form, we're restricted to looking at just its geometry. We're using geometry methods to kind of solve it and figure out what's going on, and then relating all of our things together with our time derivatives. So we're relating our S value here as some function of theta. Like we're going to use geometry like law of sines, law of cosines, all of our trig functions, using all of that together to relate our S and our angle in some way. And then if I take time derivatives, so if I take the time derivative of my position, right, if I do dt on each side to each of these things, I'm going to get some kind of velocity function, where my velocity is some kind of function of omega, right? Relating that angular position with respect to time is going to give you omega. And then if you do that derivative with respect to time, you're going to get some kind of acceleration for your angular acceleration and your linear acceleration. Some function of alpha. So essentially what we're going to be doing here in these problems that we're looking at is we're going to create a relationship between S and theta. And typically that S value is changing and that theta value is changing for these members that are pinned together. And then we're going to take take your first time derivative, so that's dt, first time derivative of that function to get a relationship between v and w, to find velocity and angular velocity. And then you're going to take a second derivative, take a second time derivative of that original s function to find your acceleration and your angular acceleration. So these are your kind of basic steps here when we're working with this. These geometries tend to get a little bit messy, a little bit complicated, which is why we don't use this absolute analysis all that much. It's usually a lot easier for us to use a relative analysis in these problems. But it's good to know, so we're going to go ahead and work through just one example problem to kind of see how this works. In this example, we can see that we have a window that's opened using hydraulic cylinder AB. So that's our rod AB right here. This hydraulic cylinder is able to get longer and get shorter as that window opens, as it rotates through this angle theta that we see here. So this window is open using a hydraulic cylinder AB. If the cylinder extends at a constant rate of 0.5 meters per second, determine the angular velocity and the angular acceleration of the window at the instant that theta is 30 degrees. So what we're doing here, what we're going to do with these absolute analysis problems is we're relating everything by geometry first in order to find s in some kind of function relationship with theta. Right, and then we can take our time derivatives and we can find that angular velocity and angular acceleration from those relationships. So the very first thing we want to do is we want to find this relationship. We want to find this s in relation to theta. And again, that s value, as we see here, s is the length of AB, and our theta is this angle the window is rotating through as it opens up. So what I'm going to do is I'm going to kind of pop out this triangle that we see here, this overall OAB triangle. I'm going to pop this out so we can see it a little better and start pulling out some information, kind of constructing a triangle, constructing a relationship here. So I can see that from O to A, my length is 2 meters. From O to B, my length is 1 meter. I know AB, that distance is s. And this angle here, theta, gives us the rest of this relationship. Remember, I'm not going to plug in any numbers yet. I'm just going to go ahead and set up my relationship, trying to relate s and theta. And one of the ways I can do this is through my law of cosines. So our law of cosines says c squared equals a squared plus b squared minus 2ab cosine theta. Right, we can't just use Pythagorean theorem because it's not a right triangle. We could in some cases use law of sines or other of the other trig relationships like tangent or cosine or any of those. We could use a combination of these. But for this one, I think our law of cosines is going to work out really well for us because, as we see here, if I start substituting values in, my c value is actually s. This a value, I'm going to use 1 for my a value. I can use the 1 or the 2. 1 squared plus 2 squared, right? Those are those side lengths. Minus 2 times 1 times 2 times cosine theta, where I have the s on one side and I have my theta on the other side so that I can simplify this and get this s in terms of theta. So here I've got s squared 5 minus 4 cosine theta. And then of course I could square root that, and this gives me this relationship. I might just leave it, I'm going to leave it like this for now with just the s squared on one side. And just knowing that I can take that square root and I can find, it looks a little bit cleaner like this. It's going to be easier to take derivatives with all of my s's on one side and my thetas on the other and not doing any square roots. Square roots are going to be a real pain for taking our time derivatives. So I'm just going to leave it like this for now and then think about what I'm trying to find here. Let's see. Finding my angular velocity and angular acceleration when theta equals 30. So I can actually go ahead and solve for what my s value is, right? Using this law of cosines, I can find that s value if I plug in 30 here. So s is going to be square root 5 minus 4 cosine 30, which gives me an s value of 1.239 meters. So that's how long this leg of the triangle is. 1.239 meters when that theta equals 30. Right, that's just some basic trig, basic geometry relationships in finding what s is. But now what we're going to do is we're going to try to take those time derivatives to find the relationship between our velocity and our acceleration using this guy. This guy right here. We're going to take him and take our first time derivative, right? So remember, we're taking the derivative with respect to time, so we're not taking the derivative with respect to theta or with respect to s. It's always going to be with respect to time, which means it's going to be some implicit differentiation here. So when I take my derivative of s squared with respect to theta, what I get is 2s ds dt, right? Because it's with respect to time. With respect to time there. So my derivative of 5 is just a constant, so its derivative is always going to be 0. Minus, and then my derivative of 4 cosine theta, the derivative of cosine is negative sine. So I'm actually going to positive 4 sine theta, and then again, it's implicit differentiation. It's derivative with respect to time, d theta dt. Which is great because I know some of these implicit differentiation guys that I got from this derivative, those mean something to me, right? ds dt means something to me. I know what that is. That's just velocity. Right, so I have 2 times s times velocity equals 4 sine theta, and then I know d theta dt. That's another one that is known. My d theta dt is just omega. It's just our angular velocity. And that's one of the things we're trying to find, right? We were trying to determine our angular velocity, so this is how we find it. We know what s is, we just calculated it over here. We know what theta is, we know it's 30 degrees, they gave us that. And then this v value here, how s is changing with respect to time, that was actually given to us up here, right? The cylinder is extending at a constant rate of 0.5 meters per second. So the way that AB is changing, that velocity there is 0.5. So I can go ahead and start plugging my numbers in. 2 times 1.39 times my 0.5 meters per second equals 4 times sine 30 degrees times omega. So I can divide that sine, or 4 sine 30 over to find that omega value. And that gives me that my angular acceleration, when I plug that in, is going to be 0.62 radians per second. Oh, so we got one done. So there's just one more to do. Right, we're going to take our second time derivative of our equation. So we can do that. We can actually just skip ahead and use this relationship here. I can use this relationship to take another time derivative, another derivative with respect to time, to find my angular acceleration. That's the last guy that I need here. So the really important thing to remember, and a lot of this just feels like calculus and, trig review, just a lot of review from math classes, they all come together for this problem, because we're going to have to remember that we've got to do product rule for this implicit differentiation, right? Because when I have this s times this v, I've got to do my product rule, right? Where I have my s times my v becomes s times dv dt plus ds dt times v. Right, that product rule where you have original times derivative plus derivative times original. That's what we've got here for our product rule. All of that is times 2 we had out there in the front. And we've got to do that exact same thing for the other side of our equation when we're taking this derivative. It's going to be 4 times our derivative of sine is going to be cosine theta dt. That's times omega. Plus our original sine theta, and then the derivative d omega dt. Right, all of those derivatives with respect to time. So I'm gonna cancel out this 2. I feel like that's gonna be easiest for me. I can cancel that 2 out with this 4, and that leaves me with a 2 on this side. And then I can simplify this sum. Right, so I've got s times dv dt, we know that's acceleration, plus ds dt, we know that's velocity. So this guy becomes acceleration, this guy becomes velocity, so I get velocity squared, equals my cosine theta times d omega dt, we know that's just omega again. So cosine theta times omega squared, plus sine theta, and then that d omega dt gives us our alpha, our angular acceleration that we're looking for. So I can rearrange this, and I can solve for my alpha. Now, one thing we'll notice even before I do that is our acceleration here. Right, what is this acceleration? Well, we have that cylinder extending at a constant rate of 0.5 meters per second, and since that velocity is constant, we're actually not going to have an acceleration for this guy. That first term is going to go to 0. So when I rearrange this equation that I've got here, I'm going to get alpha equals v squared minus omega squared cosine theta over sine theta. And I have all of those values. I can plug all of those in. And let me see, I'm kind of running out of room. Let me see if I can pop it up here. My alpha, my v squared, so 0.5 squared, minus omega we just calculated was 0.62 squared times cosine of 30 degrees all over sine 30 degrees. And oh, I dropped my 2 out front. Whoops. 2 there. There's a 2 there. That puts a 2 on the bottom there. A 2 on the top here. My mistake. I dropped too many of my 2's. Got a little too excited. Alright, I think we're all good now. I think I got everybody. So with that, when I plug that into my calculator, I get an angular acceleration of negative 0.415 radians per second squared. And so we get this as a negative term. So what does that mean? What is a negative angular acceleration? And in this case, really all that means is that our angular acceleration is in the opposite direction of our angular velocity. So our angular velocity is swinging out one way, but it's decelerating, right? It's getting slower as that window is opening here at the 30-degree mark. So as you can see, it's a lot of trig, it's a lot of calculus with some implicit differentiation. It's not the most intuitive, I would say, way to do this. What we're going to do in our next few videos is talk about how we can do these problems as a relative motion analysis, primarily using vectors, but we can do it in a scalar way too. But using our vectors is really going to give us a lot simpler way to do things, a lot clearer way to kind of define things and talk about things. So in our next few videos, we're going to be talking about general plane motion using relative analysis.